Hello friends, welcome to Engineering Made Easy. I'm Lalit Vasist. In the last lectures, we discussed about what are vectors and how to perform addition and subtraction of two or more than two vectors geometrically. Today, I will tell you how can we multiply vectors. Actually, there are many ways to multiply vectors. These are, let me write it. These different ways are scalar product, also called as the dot product, vector product, known as the cross product, and scalar triple product, and the fourth one is triple cross product. So multiplication of vectors. These are of four types. Scalar product, also known as dot product, vector product or cross product, the third one is the scalar triple product. And the fourth one is the triple cross product. Okay, so these are the four different types of products. We will deal with all of these different types of ways to multiply vectors. Today, in this lecture, I will discuss the dot product, which is also called as scalar product. So let's begin the dot product. Okay, so the definition of dot product, we can define it as dot product is a way of multiplying two vectors to form a scalar. That's why it is also called as a scalar product. So dot product is a way of multiplying two vectors to form a scalar. That's why it is also called as scalar product. Okay, geometrically, the dot product is the product of magnitudes of the two vectors and cosine of the angle between them. Okay, and algebraically, the dot product is the sum of the products of the corresponding entries of two sequences of numbers. Okay, so we will understand both of the definitions of dot product, geometrical and algebraical, one by one. So first of all, let's start with the geometrical definition. Okay, So geometrically we can represent the dot product of two vectors as let me write it. If I have two vectors A and B, if this is vector A and here is the vector B, and this is the angle theta between these two vectors, okay, then A cross A vector dot B vector, A dot B, okay, these are two vectors, can be defined as magnitude of vector A into magnitude of vector B into cosine of the angle between these two vectors A and B. Okay, it can also be written as, we can rearrange it, vector A and B cos theta, okay, or it is also same as B cos theta. I will tell you why I have written it in this way. So what is this? These are the magnitudes and theta is the angle between these two vectors. So what do I mean by this arrangement? Why I have written it in these two ways? So now let me draw a figure to explain it. Okay, if this is vector A and here I have vector B having angle theta between these two vectors, and let's call these and drop, now we drop a perpendicular from B to A. Let's call this point as Q, and here is the point P and O. So this length OQ is the projection of vector B on vector A. Got it? So what is the length of OQ? This OQ, since we know that cos theta is equals to OQ divided by OP, so it is OQ divided by vector OP is vector B. So we can say that this length OQ is equals to B cos theta. So this length we have got is B cos theta. So if I as I have written the vector A dot vector B as B cos theta into vector A, I have written it. So you can say A vector dot B vector is vector A, sorry, the magnitude of A into magnitude of B cos theta. Okay, magnitude of B into cos theta. So this B cos theta is nothing but the length of OQ, which is the projection of vector B on vector A. So we can say that this is equals to vector A, this is equals to magnitude of A multiplied by the projection of other vector A, other vector B on A. Projection of other vector B on A. Okay, in the same way we could also say that if I draw perpendicular from vector A to B, then it would be written as magnitude of B into magnitude of A cos theta. So the magnitude of B multiplied by the projection of vector A on vector B. So in both cases we can write it. So let me tell you one more thing, that if we vary the angle between the vectors A and B, then we will get some interesting results. Like let's understand it. How? If I have this vector A, and here is the vector B and angle theta. If since we know that vector A dot B, the dot product of vector A and B is AB cos theta. These are the magnitudes A and B. Okay, so if let's take few important values of theta. If theta is equals to 0 degrees, then A dot B would be written as A into B into cos 0, which is AB, since cos 0 is 1, and if so it would be just the magnitude. If the angle between these it is like something like this, A, and it overlaps vector B, so here the angle is 0 degrees. So if I take theta equals to 90 degrees, then the dot product would be A, magnitude of A and B into cos 90, and cos 90 is 0, so it would be 0. Okay, so if these are perpendicular at 90 degrees, so this is the case. So you have seen here that it is also possible for the dot product of two non-zero vectors to be 0. Here these are two non-zero vectors, but we are still getting 0 as the dot product, since the angle between them is 90 degree. So keep it in mind that we can even get 0 as a dot product if the vectors are non-zero. So let's take a very good physical example of this dot product. Where are these applicable? So we know that the work done, W, it's an example. The work done W is equals to F dot S, force into displacement. Okay, so as you can see one thing, that force and displacement both are the vector quantities, and when we dot product them, when we perform this action, this multiplication of dot, then we get work which is not any vector. It is a scalar quantity, so that's why it provides the scalar by multiplying two vectors. So we know by definition that it is equals to magnitude of force into magnitude of the displacement and the cos theta. Theta is the angle between these two vectors. Let me draw a very important and very interesting figure. If this is a box, okay, this is simply a box, and I want to slide it forward, then if I apply a force F in this direction, and since we know that if I apply force, this is the earth, the ground, so it will slide in this direction. So you understand that if I want to slide it in this direction on horizontally, then if I want to apply least force to slide it, then I should keep this angle with the horizontal, this, if it is theta, this is direction of displacement horizontally, I should keep this theta to 0. And if I keep this angle theta at 90 degrees, then it will not move forward, it will just be lifted. All the components will be in the vertical direction of this force. Since this force has two components, as you can understand it, that this, if I am applying here force F, and here is the angle theta, then it has two components. In this direction it has F cos theta, and in this direction it is F sin theta. So only the F cos theta is used to move it horizontally. Okay, so by the definition of dot product, we know that since W is equals to Fs cos theta, then if theta is equals to 0, if theta is equals to 0 degrees, then it would be equals to F into X, S. Okay, then W would be Fs, since cos 0 is 1. But if theta is equals to 90 degrees, then W would be equals to 0, since cos 90 is 0. As you can see that if I keep this angle theta to be 90 degrees with this horizontal, then the work will not be done, because it is not in the direction of, it will not move in any direction. The direction of this force and displacements are at 90 degrees, so it will not move horizontally, so the work done would be 0. These are the two vectors are at 90 degrees. Okay, and if I keep the theta at 180 degrees, you can understand it also. If theta is at 180 degrees, then the W would be minus of Fs, since cos of 180 would be minus 1. So the box will move backwards if I keep this at 180 degree. Okay, so now we know the dot product geometrically. Now we will understand the same concept of dot product algebraically. Okay, so now I am going to tell what is a dot product algebraically. So let's draw a figure. If this is vector A and here I have vector B, and this is angle theta between these two vectors, and we also know that vector A dot vector B is magnitude of A into magnitude of B into cosine of the angle between these two vectors. Okay, so let's suppose that vector A is equals to AXI cap plus AYJ cap plus AZ K cap, and vector B is equals to BXI cap plus BYJ cap plus BZ K cap. So here this I cap, J cap and K cap, let me write it, I cap, J cap and K cap are the unit vectors in X, Y and Z coordinate directions. Okay, and this ax, ay, az are the components of the vector A in x, y and z directions, these three coordinates x, y, z, and similarly bx, by, bz are the coordinates along component of the vector V along x, y and z. Okay, so and also these A and B are the magnitudes of vector A and B, so we represent the vector, this magnitude of A as under root of ax square plus ay square plus az square. Similarly, the magnitude of B can be written as bx square plus by square plus bz square. So also the magnitude of a vector is sometimes also called as modulus of the vector. In this way you can find it. So let's take an example to explain this whole process, how we can dot multiply two vectors. So let's take an example, simple example. If vector A, let's suppose vector A is equals to 3i cap plus 2j cap plus, let's take k cap, and vector B 2i cap plus j cap plus 3k cap, then I want to find A dot B. Then 3i cap plus 2j cap plus k cap is dot producted with 2i cap plus j cap plus 3k cap. Okay, so it is like 3i cap it can be written as, you know, okay. So now listen, when this 3i cap is multiplied with all these three, then we know with the definition of dot product, we will dot product this 3, we will multiply this 3 and 3i cap and 2i cap, since these are two vectors. Understand it at this, in this corner, let me explain it separately, that here 3i cap and 2i cap. Okay, so this is the just the dot product, then it is the magnitude of this vector into magnitude of this vector and the cos of the angle between these two vectors. Since these are along the x-axis I cap, so the angle is 0, so it is simply the 6. But when I will multiply this 3i cap with this j cap, then you know it is the magnitude of this vector multiplied by the magnitude of this vector into cosine of the angle between these two vectors, which is 90 degree. I cap is along x-axis, this is along y-axis, so it would give us 0. So we can write it as, so keep it in mind, the corresponding vectors along which are along the same direction would give us just the product of the magnitudes simply, and in other case it would be 0. So we can write it simply as 6 plus 0 plus 0. This is 6, this is 0, this is 0. Similarly, this would give us this 2j multiplied with 2I cap would give us 0. So it is 0 plus 2 plus 0, and in this case it would give us 0 plus 0, this would be 0, this would be 0, and this would give us 3. Okay, so it is 6 plus 2 plus 3 equals to 11. Okay, so we can directly do it also as, so we can directly write it also. You don't need to do it all, just simply multiply them, corresponding values, this to this, I to I, j to j, and k to k, simply as 3 into 2 plus 2 into 1 plus 1 into 3. Okay, so it will give us simply 6 plus 2 plus 3 equals to 11. Okay, so friends, this was all about dot product of vectors. We have seen both the cases, geometrical and algebraical. Okay, in the next video I will discuss cross product of vectors, also called as the vector product. So please friends, like the video and share it if you liked it, and please don't forget to subscribe the channel Engineering Made Easy. Thank you for watching. Have a nice day. Bye bye.